You've completed Gaussian or Gauss-Jordan elimination, and now you need to interpret the result. No worries, for both processes, there are three potential outcomes that can be identified the same way. Your outcome will either have one unique solution, an infinite number of solutions, or no solutions. The way we identify the outcome is based on the pivots within the final result of the elimination process. Recall, the pivot is the first non-zero entry in a given row from left to right. So for all three of the scenarios, here are all the pivots. A column that contains a pivot is called a pivot column. All of these columns are considered pivot columns since they contain a pivot. Now let's look at the pivot columns for the three scenarios. In our top example, every column on the left-hand side is a pivot column, while the right-hand column is not a pivot column. When this happens, our system of equations has exactly one unique solution. For the second scenario, there is one or more columns on the left-hand side that are not pivot columns, while the right-hand column is still not a pivot column. When this happens, our system of equations has an infinite number of solutions. For the final scenario, if the right-hand column is a pivot column, which happens when the left side of the row is all zeros, and the value on the right column is not a zero, basically when this happens, we call our system of equations inconsistent since it has no solutions. There is no combination of values for our variables that satisfies our system of equations. Now that we talked about how to identify the number of solutions for a given system of equations, let's talk about an example for each scenario. Consider this starting system of equations. Here is the augmented matrix associated with this system. Each column of this matrix on the left-hand side represents one of the variables in our system of equations. The column to the right of this dotted line represents what each equation was equal to at the beginning. If you need a refresher on setting up the augmented matrix, check out this video here. To find all the solutions of this system of equations, we can perform Gaussian elimination, which would give us this result, or we could do Gauss-Jordan elimination, which would give us this result. For each one of our scenarios, everything was kind of based on pivot columns, so let's find the first non-zero number within each row from left to right. It looks like for both results we have three pivots. There is no pivot in this rightmost column. Since there's no pivot in the rightmost column is not a pivot column, which tells us that there at least exists one solution for our system of equations. So we can exclude this third scenario. We either have one unique solution or an infinite number of solutions to our system of equations. Is every column to the left of the dotted line in our final results a pivot column? Yes, every column to the left of the dotted line contains a pivot, and so each column is a pivot column. This means that our system of equations has exactly one solution. How do we find this one solution? Well, we can find it using either of these resulting matrices we got doing the elimination process. Remember, the columns of these matrices are associated with the variables x, y, and z of our initial system of equations. The first column of the result is associated with x, the second column of the result is associated with y, the third column of the result is associated with z. In the column to the right of the dotted line is what each of those rows will be set equal to. Looking at this system on the bottom, we see 0 multiplied by a lot of different variables. All of these we know are equal to 0, and so we can reduce this bottom system of equations to this. Notice, this gives us the unique solution. The top row tells us that x equals 1, the second row tells us that y equals 2, and the third row tells us that z equals 3. Similarly, this top system will get us the same result. Starting with the bottom row, we see that 13z equals 39. Dividing by 13 on both sides, we get z equals 3. Going up to the next row, we have 7y minus 14z equals negative 28. But we already know z equals 3, so we have 7y minus 14 times 3 equals negative 28. This gives us 7y minus 42 equals negative 28. Add 42 to both sides and we get 7y equals 14. Dividing by 7 gets us y equals 2. Finally, for our top equation, we can sub y equals 2 and z equals 3 into it since we've already found those two variables. This will give us 2x minus 4 plus 15 equals 13, which is 2x plus 11 equals 13. Subtracting 11 on both sides, we get 2x equals 2. Dividing by 2, we get x equals 1. This process on the left is called back substitution. So, x equals 1, y equals 2, and z equals 3 is the unique solution for our initial system of equations. To check that it satisfies this system, we plug these three values into the original system of equations. So we plug 1 in for x, 2 in for y, and 3 in for z. We check that when we simplify this now, that the left-hand side of the equations is equal to the right-hand side of the equation. It looks like for all three equations, both sides are equal. So, x equals 1, y equals 2, and z equals 3 is the only solution to this system of equations. To write this answer in set notation, we would write it as this. Let's move on to another example. Consider this system of equations. It can be rewritten as this augmented matrix, where once again the columns are associated with the variables of the system of equations. Using Gaussian elimination or Gauss-Jordan elimination, we would arrive at these two resulting augmented matrices. Based on these resulting matrices, how many solutions does this system of equations have? Well, let's first identify our pivot and pivot columns in these resulting matrices. It looks like we have two pivots in each matrix. None of the pivots are located on the right-hand column, and so we know that solutions must exist for our system of equations, so we can ignore that third scenario. Are all the columns to the left of the dotted line pivot columns? No. In both results, there is a column to the left of the dotted line that is not a pivot column, and so we know that our system of equations will have an infinite number of solutions. We can cross out the first scenario. How do we find the infinite number of solutions? Well, it is a little similar to the process we did for the unique solution, except we handle the columns that are not pivot columns in a little bit of a different way. Every column that is not a pivot column, we are going to allow to be any number from negative infinity to positive infinity. We call these variables free variables because we allow them to roam freely among the real numbers. Since we allow them to take on any value, we represent this freedom by setting them equal to a parameter value, normally t, and we allow t to be any real number. So the column associated with the variable z is not a pivot column, so z is a free variable, and so we set z equal to t and let t be any real number. So z equals t. Now, let's use the second row of the Gauss-Jordan result to find what y is defined as within our set of infinite solutions. Well, the second row is equal to y minus 1z equals 5. Z equals t, so we can replace z with t, which gives us y minus t equals 5. Isolating the y, we add t to both sides and we get y equals 5 plus t. When we have free variables, the variables associated with the pivot columns will contain the free variable parameters within their solution. So y equals 5 plus t is acceptable, and we'll revisit that shortly. Finally, we use the top row to get what x will be equal to within our set of solutions. The top row gives us x plus 1.5z equals 1. We replace z with t, we get x plus 1.5t equals 1. Isolating x, we get x equals 1 minus 1.5t. So we have x equals 1 minus 1.5t, y equals 5 plus t, and we have z equals t. So where are the infinite solutions? Remember, we said t could take on any real number. So if we let t equal 0, t equal 10, or t equal 100, we would get different values for x, y, and z. Each one of these solutions will satisfy our original system of equations. If we plug any of them into the original system of equations, we'll see that the left-hand side is equal to the right-hand side. So for each value we select for t, we will get a different solution. So basically, the infinite solutions come from the free variables being able to take on an infinite number of values. Each time we select a value for a free variable, it is connected to a valid solution to the original system of equations. We can represent the set of solutions here with this notation, where here on the left, each position is associated with a variable from our system of equations, and on the right we have the values that our free variables can take on. Let's look at one final example. Consider this system of equations, its original augmented matrix, and the resulting matrices we get when we do Gaussian or Gauss-Jordan elimination. How many solutions does this system of equations have? Well, let's first identify our pivot and pivot columns. What do you notice about the column to the right of the dotted line? It contains a pivot. Therefore, there is no solution that satisfies this initial system of equations. This bottom row represents 0x plus 0y plus 0z equals a non-zero constant. 0x, 0y, and 0z is just 0. 0 added together 3 times is just 0. So for both of these final results, we essentially have 0 equals a non-zero constant. Consider the result we get from Gaussian elimination. Does 0 equal 68? Well, no. For the Gauss-Jordan elimination case, does 0 equal 1? No. Basically, we have something that is not true within our resulting matrices, making it so that no solution exists. We call this an inconsistent matrix. Ultimately, after you do Gaussian or Gauss-Jordan elimination, you can determine which of these 3 situations you have on your hands based on where your pivots are located within your resulting matrix. I'm Joe, and thanks for spending some time with me.